Hello everyone. This video is for the completion of a Coursera course on machine learning foundation for product managers. The objective of the task is to predict the net hourly electrical energy output for a combined cycle power plant with the given independent features: temperature, ambient pressure, relative humidity, and excess vacuum. So without delay, let us start on the dataset on this project. First, import some of the libraries that we will need, pandas, C1, and some of the APIs from scikit-learn. Load the data. So here we see 4 independent variables: ambient temperature, vacuum pressure, ambient pressure, and relative humidity. And the fifth column, P, is our targeted variable, that is the net energy output. Let's check the quality of the data, missing values and NaN. We see that there is no NaNs and there is no missing values. Now let us see how these data variables are correlated with each other. Since PE is our targeted variable, let us see each variable compared to PE. So the temperature, using all the data, it's 95% correlated. The vacuum is 87% correlated. They both are negative signs. That means inversely correlated. Air pressure is 52% correlated, moderately. The relative humidity is 39%, the correlation coefficient. Is somehow correlated, not very strongly. So with this understanding, let us create a linear correlation, linear regression for our case. This is a case of linear regression, right? Now, let us first split the data into train set, validation set, and testing set. So the train is training the model, validation is initial testing of the model. So we'll be looking at different models, we'll be hyper-tuning different parameters, and once we are satisfied with the model, we'll finally select one of the different experimented models as our prediction model, and we'll use the test data to test the final model. So first, X is our independent variable. It consists of 4 features, except the targeted variable P, and then Y is our targeted variable. We split our dataset into train and test first in the ratio of 90:10. And using the training dataset, we'll again split into train and validation in the ratio of 75:25. So let us look at the data distribution here. We have the train data 6,458. We have the validation data 2,153, and we have the testing data 957. This looks pretty reasonable. Now let us construct a simple linear regression. We use, so let us first use the simple linear regression. Here in the first case, let us use each of the features one by one and see how the result looks like. So when we use air temperature, vacuum, air pressure, and relative humidity one at a time, here is the result. The temperature is 90% correlated with 5.5 milliwatt as the root mean square error. This is the highest, highly correlated feature. And relative humidity is least correlated. And this agrees with our heat map that we saw earlier. Now, let us check, since AT and V is quite highly correlated, let us check first these two features combined, and then next let us use all the four features combined and we compare the results. So if we use AT and V as the two features, we see 91% as the correlation coefficient and 5.05 as our root mean square error. This is improved result compared to, a little bit improved compared to using single variable. Now, again, if we use 4 variables, all the variables at once, the result is improved a little bit more. 93% correlation coefficient and 4.61. So the R square increased a little bit and RMSE decreased a little bit. So this is a little bit of improved result. Now, since the data set has a range, right? Like what we see here is the range is more pronounced, but if we look at the data here, see, like the temperature ranges from 14 to 20 or even more, 25 or even more. So we need to normalize this data set. So let us build a pipeline to normalize this data and then run the regression model. So let us normalize. We have a pipeline using the standard scaler. We normalize it, and we have linear regression. We feed the train data, and then we use the test data. Test data means here the validation data to test the model. So we see here the result is R squared is 0.93, while RMSE is 4.61. This is same as when we used the linear regression, all four features without normalization. The result is same. Now let us compare our result with support vector regression. We have the pipeline where we normalize the data, and then we use SVR with the coordinate is equal to linear and C is equal to 0.01. We can use different values of C. We start with, let us say, 0.01. So if we run this, we see that the correlation coefficient is 92% and RMSE is 4.97%. Here, if we compare this with our linear regression, the result for SVR is a little bit degraded. I mean, linear regression has a little bit better result. Now we can play with different experiments using different values of C and check the result. I did it offline, and the result doesn't improve significantly. I saw that linear regression is better than SVR in this given scenario. So, and also as we increase different hyperparameters, the computational time for SVR increases. So given a little bit better result of the linear regression and computationally SVR being expensive than linear model, I choose to use linear model as a final predictive model to predict the net hourly electrical energy output for the plant. Now, using the test data that we separated in the very beginning, the test data, 10% from the data set. Where is it? Yeah. So this test data, X test, let us use the test data to check the final R square and RMSE of our data set. So we see that R square is 0.93 and RMSE is 4.36. The result is similar to the training and validation data set. So we do not see any overfitting or underfitting of the data here. And the correlation coefficient is pretty high, and RMSE is quite good, quite acceptable. So I think that the linear regression model developed in this project can predict the energy output from the combined power plant pretty accurately. Thank you.